Good morning, everyone. You're all doing well. I apparently slept through a storm last night based on what it looks like outside. Hopefully, no wind or feelings or too big of a news to everyone. So, today we're going to continue with Chapter 8. We talked about the first law of thermodynamics in detail, right? W, U minus W. Is that where we left off? Okay. We're going to continue with those. We'll finish up Chapter 8, probably tomorrow, and then we'll you should already be working on your Chapter 8 assignments. They're currently due next Tuesday. So, after we finish up Chapter 8 tomorrow, if you have any questions about your assignments, you have some time to ask those. Additionally, Chapter 8 assignments are all due next Tuesday. And next Tuesday, we'll begin moving into you for Test 2, which will be in Chapters 5 through 8. As a reminder, we do not have any labs at all next week, so that you have time to submit with us. We also we won't have in-person meetings on next Tuesday, because that is Election Day. So just make sure everyone can vote, including myself, actually. So we will have remote meetings that day for those who meet for review purposes. Just a brief reminder of the schedule. Any questions before we get started today about anything at all? Schedule or Chapter 8 or anything else on your minds? Okay. Please ask any questions you have at absolutely any time. They can be about anything. Yeah, hope you're all having a good day. The weekend's nearly here. I'm very excited for that. So, we left off. We talked about first law of thermodynamics, and I believe we looked at these sample questions. So, brief summary of the first law again. Conservation of energy. Energy cannot be created or destroyed. Any energy that enters the system has to be accounted for as to end up somewhere. If an object gains an amount of energy and only uses some of it to do work, it retains the rest of it as thermal energy. If you perform a task, say you eat 2,000 joules, and then you do you eat 2,000 joules, you perform a task that is 1,800 joules, you have 200 joules left over, which is addition. Now, that's first law. We're going to start looking at the other laws in detail as well. The second law is where we begin talking about the concept of entropy. And again, sort of the elevator pitch for entropy is chaos and disorder. Not like civil chaos, more so thermal chaos, the thermal energy in an object contributing to the random movement of its particles. The entropy of the entire universe as a whole is constantly increasing, because every single thing you do creates some amount of thermal energy that's going to make the particles involved start moving more randomly. Every action will do this. Some thermal energy will be created every single time something happens, which drives the entropy slowly upwards. A single process might be completely efficient and not create a new entropy, but you can never drive the entropy of the entire universe down. You can either maintain it or increase it. And to sort of summarize that rather colorfully, there are some processes that you just can't undo. In doing the thing, you create some amount of entropy that you cannot reclaim. Once energy is lost to entropy, you can't really use it to serve much of a purpose anymore. It's now just making things warmer, and we just have to deal with it. Now, there's some math for entropy that we are going to examine, just a little bit. So these formulas are connected to the second law of thermodynamics. The first formula up here, change in entropy, is defined as the change in an object's thermal energy divided by its temperature as it acquired or lost that thermal energy. Entropy often gets shortened as a variable to a capital S. And since we're dividing energy by temperature, the units would be joules per Kelvin. So this simply tells you how much a single object's entropy changes based upon how much thermal energy is added to it and its temperature. That was a weird noise my character made. So, this statement down here, the change in all of the entropy of the universe is always greater than or equal to 0. This is basically just the second half of that law put into an almost formula. Looking at the entire universe system as a whole, no process can produce entropy as we currently understand it. The process is completely efficient, it won't make any new entropy, but you cannot destroy entropy that already exists. You can move it, but you can't destroy it. So, really quickly, we're going to add 10 joules of thermal energy to two different objects. One of those objects is at 0 degrees Celsius and the other is at 100 degrees Celsius. So one is melting, one is boiling. They're both gaining the same amount of thermal energy, but the question is, which one's entropy is going to increase the most due to this change? So, we have our formula, change in entropy, which is exactly what we want to find, equal to thermal energy transfer divided by temperature. So, the first object is going to gain 10 joules, and it is at 0 degrees Celsius. Should we put a 0 here?
You can't divide it by 0.
You're correct. And given the fact that we can, like, if we plug the 0 in here, it'd be saying that no entropy was created by this task. 10 divided by 0 would give you a calculator error, but we understand it to equal 0, basically. So if we plugged in 0 Celsius here, we would get a change of entropy of 0, which doesn't make sense if every action drives entropy upwards. Additionally, things can be even colder than 0 Celsius. So, what should we put there instead of 0 Celsius? So what's the temperature unit that works every single time, no matter the formula? Kelvin. And, brief refresher, to convert something to Kelvin, you take the Celsius temperature, you add 273. So what's 0 Celsius in Kelvin? Very good. So, for the object at 0 Celsius, it's going to gain 0.037 entropy units from this exchange. It would technically be joules per Kelvin. Meanwhile, we have the warmer object. It's going to gain 10 joules, and it's at 100 Celsius. What's that going to be in Kelvin? Very good. Now we're dividing 10 by a larger number. So is our answer going to be bigger or smaller than the other one? So when you divide by a larger number, the answer ends up being smaller. So 10 divided by 373 is going to give us 0.027 entropy units. So the entropy of the colder object increased slightly more from the same interaction. The reason for this is just that the 100 Celsius object is already more chaotic, more entropic already. So we can convert the word chaos into chaotic to describe something that has a lot of chaos. So we can do the same conversion to entropy to create the word entropic. A system that is entropic has a lot of entropy in it. So if I say that word again, that's what I mean. So colder objects do tend to become more chaotic from the same amount of thermal energy being added to them. The 100 Celsius object is already pretty scrambled on the molecular level. Its particles are already bouncing around a lot. This change in thermal energy is not going to increase its entropy level as much as the colder object. So entropy is always rising. How much entropy one thing gains does depend on its existing temperature. As a result of this, we tend to try to vent excess heat into a heat repository. Like if you are working on a mechanical process, you usually have a heat sink that you try to put all the thermal energy into so that it's not occupying the rest of your system and making things break down and get more chaotic. I and other people, if you build a computer, odds are your machine has to have some method for dealing with thermal energy increase, temperature increase. Because if you don't, every single process adds more thermal energy to the system. Eventually your computer's going to heat up, and if you're lucky, it'll turn off. If you're not lucky, it'll melt itself. Most systems need some method to take the thermal energy that is produced out of the machine and put it somewhere else. So the concept of a heat sink is where you dump all the thermal energy so that it's contained, and since it's already hot, the entropy increase is less of an issue than it would be if that thermal energy was in your computer melting wires. Similarly, car engines have coolant systems with the same purpose. You don't want the heat of the engine because it's going to melt things. Now, questions so far? Okay. Now, this will segue us directly into the third law of thermodynamics. Entropy for the whole universe, as looking at every ounce of entropy in our entire plane of existence as we understand it, is either constant or rising. Basically, every single process creates some amount of thermal energy and creates some amount of entropy if you look at the entire universe as a whole. Now you can, however, reduce the entropy level of a single object at a time. And essentially you do this just by lowering its temperature. When you cool down a specific object, you are making its particles have less thermal energy. They're not moving around as much anymore. That means that they have less chaos, less disorder, less entropy. So the third law states, as the temperature of a single object approaches absolute zero, its entropy level will also approach zero. Absolute zero is the coldest temperature that you can have. It's the point where an object has no thermal energy left. And if it has no thermal energy, then its particles are locked in place, not moving. They are the most organized they can be. They form into as regular a structure as is possible for that particular solid, and they stay there. If they're not moving, they're not chaotic. They're as organized as is physically possible. So at absolute zero, you would theoretically have zero entropy, but only for the one object at absolute zero. In order to get it there, you had to remove all of its thermal energy and put it into some heat sink, which now has more entropy because of that fact. So this law works for single objects at a time, whereas second law refers to the universe as a whole. And we can kind of see this principle working if we look back at this formula we just talked about. If you plug in absolute zero as your temperature, you'd be dividing by zero. No entropy at that temperature. It just equals zero no matter what else you plugged in. Okay. Now, every single process creates some amount of thermal energy. How much it creates depends on a principle that we refer to as its efficiency. We were looking at some samples yesterday where you put thermal energy into something and it does a specific amount of work. The human body works very similarly. You ingest energy in your food, your body breaks that food down so that you can use the energy. But as shown in actually all three laws so far, usually not every single joule of that energy gets used for the intended process. Some of it kind of always ends up becoming thermal energy due to friction in some part of the mechanism. In your own body, for one thing, you're a warm-blooded organism as a human being, and that means that your body intentionally goes out of its way to use some energy to create heat to keep you warm and regulate your temperature. It's one reason why we can be awake during the winter and most reptiles are hibernating. Reptiles are cold-blooded, they don't make their own heat, they can't stay awake in the cold months. So by default, the human body is already designed to be pretty inefficient because we want to make heat to keep ourselves warm. It does make the summer months kind of unfun though. But in addition to that, every time you move your arm, there's various parts inside your arm that are creating friction against one another. The bones in your joint, probably your muscle tendons sliding across one another. All of that friction is going to burn energy that could have been used for mechanical processes and just convert it into thermal energy. Now, when we talk about the efficiency of a task, we're talking about how much work you get out of the machine versus the energy you had to put into the machine in order to do it. And the formula for that, inf, which, again, I don't name these variables. I wish I did. I'd come up with better terms. Inf is our efficiency ratio. So it's, we have like first, second, and third. You take the number and you add some letters next to it to sort of put it into a ranking system. Nth is usually the term we use when we don't know the number of the ranking. So first, second, third. This is the equivalent for that when you don't know what number it is. So like to the nth power is, it's some power, I just don't know what it is, and this is what its ranking would be if it had a number. So that's what this typically means if you happen to see this in any of your algebra or calculus classes. And what it represents here is the efficiency constant or coefficient for the process. It's a percentage that tells you exactly how efficient it is. If you have an nth of 0.8, that's 80% efficient. That means 80% of the energy you put in actually gets put back out as work. You find this coefficient by dividing the output by the input. This is the energy you put into the machine to make it do its job. I'm sorry, back up. This is the energy you put into the machine to make it do its job. This is the input, this is the fuel. The top out here is the output. This is what actually happens as a result. So, So, let's say that in a single, like in a meal, in a snack, you eat 2,000 joules worth of food, and then you do 1,200 joules worth of work. This is the energy you consumed. This is your output. This is the energy that you utilized successfully to perform that task. Now, what would the efficiency of this human, if we were looking at this human person like they were a machine that was using energy to perform a task, what would the efficiency of this particular mechanism be? Yes, so if we divide these two things, we would get an answer of 0.6. That means 60% efficient. 60% of your input becomes output. The remaining 40% was just converted into thermal energy and loss, or is now just warming up the machine and not doing anything productive other than keeping it warm. Every single mechanism, be it mechanical or biological, every single process, every action has some efficiency. And you're just comparing, it helps you figure out how much energy was taken away from the system by friction, basically. So if this was a human, 40% of their energy would be lost to thermal energy. It's not a very complex formula. This is a very weird way to write the variable. Any questions about this principle so far? Okay. So, quick example. Historically, a lot of our machines have been powered by burning something, which is unfortunately a pretty inefficient means of creating energy. Fire is a chemical reaction that takes stored chemical energy and transforms it directly into thermal energy. We are able to use that thermal energy to perform some specific tasks. You can boil water, and then it creates steam, and then you can spin a steam engine in an electrical plant or an old train. But because you are creating fire, it's going to create a bunch of thermal energy that's going to go everywhere, not just into the tank of water you're trying to boil. So burning is inefficient because not all the energy you're creating actually ends up in the water you're trying to boil, let alone losing things to friction later in the machine. So let's examine this type of a situation. 1 whole kilogram of coal contains 24 megajoules worth of energy. A big capital M for the prefix represents mega. And since that's not a prefix we use super often, the standard ones, kilo, hecta, deca, base, deci, centi, milli, these are all spaced 10 units apart. After kilo, we skip a few, and then we have mega. It's kilo, mega, eventually giga. And you might notice that those are scaling up in the same way that they do in a computer. You have bytes, kilobytes, megabytes, gigabytes. Use the same prefixes there and they scale up about the same way. The jump from kilo to mega is 1,000. We don't have little baby steps in the middle here. We didn't bother to name them, to my knowledge, like we named hecta and deca. So this jump is times 1,000, which means that from base to mega is times 1 million. So 24 megajoules is how many joules? 24 million. If you're going from mega to joules, you multiply by 1 million. And this unit comes up a lot of energy because we tend to need a lot of energy to power everything we do as humans. So, 1 whole kilogram of coal, which is a lot, this would be a pretty big cube of the stuff, can contain up to a total of this much energy. This is all energy that's sealed within it in chemical form. If you set that entire block of coal on fire and say it is powering a steam turbine, your goal is to use that thermal energy to run a steam engine in order to accomplish a task, like running a train, and it performs 10 megajoules worth of work. First of all, how much of the burned thermal energy has now just become internal energy, thermal energy in parts of the mechanism? $14 megajoules of energy. You're right. You're absolutely right. So, if we wanted to get technical for the notes, delta U equals Q minus W. Internal energy increase is the delta U. Delta U equals, we're adding 24 megajoules, but we only do 10 joules worth of work. Why did I write it? It's supposed to be. I am apparently still so. The internal energy of the system increases by 14 megajoules. That's over half of the energy just lost making things more. And honestly, that's being generous for this sort of a process. Most of humanity's machinery, especially generators, are incredibly inefficient. You're lucky to get like 20% of the energy in a fire actually doing some work. Because again, every single thing touching the fire gets warm. That includes whatever you've got it sitting on. That includes all the air around it. If you get really any of it into the machine that you're trying to run it with, you're probably lucky. And this unfortunately includes cars. They are very inefficient because they're literally causing just an explosion in their engine. It creates a lot of heat and relatively little thrust. Now, this is how much energy gets wasted. What is the efficiency of this particular system? So, efficiency is output divided by input. This machine is going to do 10 megajoules of work after we burned 24 megajoules worth of energy. I keep setting things down when I need them. Alright, so that is, if you just plug this into your calculator, and since we've got megajoules on the top and megajoules on the bottom, those will cancel out and you get the same answer that you did joules. Your safest bet is usually to convert to the standard unit. That would be joules for energy, but we're just dividing one by the other, so the units are going to cancel out anyway as long as they match. So ultimately, 10 divided by 24 would be the same as 10 million divided by 24 million. That's going to give us 0.4167, which comes out to 41.67% efficient. That's actually higher efficiency than most machines. I think, just as a sense, just to give you guys this information, I'm not a biologist, so please temper this factoid with an entire salt packet's worth of salt. But I think the human body, in terms purely of mechanical energy output versus the food you eat, is only about 20% efficient. If you eat 20 joules worth of energy, you might get 1 joule of mechanical energy out of that meal. That's what I last was told, and I don't have any other data to support or debunk that. But I'm under the impression about 80% of the energy you eat ends up as thermal energy, either due to your body directly burning it to keep you warm, or due to friction in your bones and muscles. So we're already not very efficient. So that whatever engine over there is actually about 42% efficient, that's a masterpiece. You're lucky to get that high. Now, if a machine hypothetically was able to output every single joule of energy that you input into it, it would have an efficiency level of 100%. That is the only time that entropy would not increase in a process. If you have a 100% efficient machine, no energy would be lost. Everything out, everything in just goes right back out, and entropy wouldn't increase. But no real process involving actual matter in the universe is that efficient to our knowledge. If you could build a machine that was 100% efficient, we call that perpetual motion. Because if it didn't lose energy over time, it wouldn't slow down, it would just keep running. Perpetual motion is like the holy grail of a lot of physics. Like, it would be wonderful if we had it, but mechanically it probably, people are still searching for a way, if we can even physically create it ourselves. So when I say efficiency, when I talk about the efficiency of a task, we're referring to how much energy actually gets used for its intended purpose. Any questions so far? Okay. Yes?
So this, I know this is like in fossil fuels and stuff, what about like electric cars? Is the efficiency of them higher?
Electric machines do tend to be more efficient than ones that involve combustion. Combustion being technical word for setting something on fire. But they're still not perfect because every single electrical gadget still has physical parts and gears and cogs that run across each other, and thermal energy even builds up in the wires when you run electric current through them, which is why light bulbs are hot, don't touch them. So they tend to be more efficient, but although one issue with electricity is A, it does create thermal energy naturally over time, B, batteries are heavy. Like, if you were to look at joules per pound of storage unit, gasoline has more energy per pound than a battery does, because most batteries are made of lithium, which is rare and expensive and heavy, which is one reason why electric cars don't have a very good range to them. Like, you charge it up, you can maybe go 200 miles and bring the juice back up, because if you had a battery in it that would last the same amount of time as a normal tank of gasoline, it would weigh way too much to actually be able to drive itself. So there's pros and cons to each. We don't have the best answer yet. Yes?
I I mean, on that point, yeah, I think they are way more efficient because they have like 100% torque at 0 miles an hour. So you can use like all your power at once in an electric car.
Right. In an electric car, if you are parked, you can go from parked and press the pedal. I guess it's not really the gas pedal. You can press the go pedal, and immediately the engine can put all of its work into going to max torque, and you will take off as fast as you can from stationary. But in a combustion engine car, you usually need to slowly go into it. You need sometimes to cause a few explosions to actually get you moving forwards. Yes, they are more efficient, but they do still have their own problems because you are still going to lose energy every single time one gear touches another gear, or when your tires touch the road, or when wind touches your windshield, or when you sneeze. Literally everything will take energy out of the system.
I thought they didn't have like transmissions, like Teslas didn't have transmissions.
I have not researched
a
it.
single gear.
Theoretically, I could see why that would be the case. You wouldn't really need them. You control the speed just by changing the current, the voltage. So, yeah, I don't see them needing gears, which would also increase their efficiency. And the main issue with electric cars is mostly the battery. Electricity is more efficient than fire, but batteries is heavy. It's expensive. Honestly, your entire phone, the battery is one of the more expensive single parts. Anything else? I do welcome oddball questions. Interesting discussion. Now, we're nearly to the end of chapter 8. We only have about one more formula, one more principle to talk about. And since this lecture is going to meet again tomorrow, I'll leave it to you guys. Do you want us to start it now so that there's less to do tomorrow? Or we can just break here if you guys want to, and we can lost my train of thought mid-sentence. We can break here and finish it up entirely tomorrow. Do you guys think?
I'd rather just break here.
Okay. Everybody sleepy? Okay. Now, as you're packing, just so that you're aware, what we're doing next is we're looking at conduction and thermal energy flow. We're going to be talking about whether something resists thermal energy flowing through it or allows it to pass easily. For example, styrofoam is an insulator. Thermal energy does not pass through it easily. We're going to look at why and the math behind it, as opposed to say metal, so it does pass through it easily. So, be working on your Chapter 8 assignments. Questions. It helps all of us if you're not doing it Tuesday night. I'm calling out any humans, if there's any specific human, I get you notes for everyone all the time. And helps everyone if you go ahead and do it. Thank you all and have a wonderful day. Right now, your grade is just pretty much entirely on a spreadsheet that I possess. And if you want to know it, I will gladly tell you it. I just need to pull up the spreadsheet and crunch the numbers.
Time right now. I mean, maybe tomorrow or some other time. I mean, it's like no rush. I'm just gonna like ballparking. I mean, it's not a big deal.
Remind me your full name.
Grady Copter.
Your midterm was a 97.
The grade at midterm?
Yeah.
Okay.
Well, you got 100 on the test. Your homework quiz grade is.
That last question went surprisingly well. I thought I only did part of it. I don't know if you gave me credit for that, but that one, I mean, everything else I felt confident on. But that last question, I was like, there's no way I had. But then I remembered we had those extra, I think it was extra 10 points that helped.
That last question was designed to be the hardest one, and it was worth 20 points, meaning if you got half of it right, you could still get 100.
Right. So I was glad with that. But yes.